All right. I just posted it, so I'll just start the class anyway. Yeah, let's get back to the point. Yesterday, I talked about, I ended the topic introducing thin film interference to you, right, people, right? So I'll just give a heads up what actually comes before this topic. I needed to talk about the reflection of light. Do you remember this bit where we talked about a wave going and meeting a rigid end and going from a rigid end to free end, like a lighter medium to stronger medium or stronger medium to lighter medium, right? In these cases, there was no phase difference of any of the waves except for one situation where the wave is going like this and hitting a rigid medium and reflecting with a phase difference of pi. Okay, everything else remains same. In this case, in this case, in this case, the incident, the transmitted, the reflected, incident, the transmitted, and the reflected. This is incident, transmitted, and reflected. We know about these things. I've talked about these things. You don't really need to worry about it. There is only phase change in one simple case when a wave is going from a lighter medium to heavier medium and reflected, the phase difference is pi. That is the only part that you need to remember. It actually goes the same way with the light also. Let us say when you are traveling from a thin medium, let us say a vacuum, to glass slab. When the light is hit, some part is transmitted, some part is reflected. The reflected part is clearly created a phase difference of pi with the initial one. The initial one it's already created a phase difference pi. This one didn't. The phase difference is zero only. If it is zero, this is zero, this is pi. But the same thing, the same ray, when it goes out of the glass, the same ray when it is glowing glass to vacuum again, let us say. It is going from glass to vacuum and is reflecting and transmitting. Here, all the incident is zero, this is zero, this is zero. Nothing is creating any phase difference. Okay, there is only one case where there is a phase of pi is created. So we should be careful with only one specific ray, which is going from a thin medium to reflecting at a thicker medium, like reflecting at a glass medium. Only about this value. Okay, so you should be consider about that. You should really be careful about that. So if someone gives you an equation saying E naught sine omega t minus kx is a wave, sine light wave hit a glass slab, what do? You additionally you take the reflected wave and you additionally add pi value in the phase. For rest of those things you don't have to add anything. They just remain the same things. Now the reason why I'm telling you this is I am considering a small thin glass slab or thin soap film or anything it could be. It's a different material. Let us just call it as a glass tube, glass slab. Later we consider the thin films also. So there is an incident ray. Some part is reflected, some part is transmitted. Some part is reflected, some part is transmitted again. Some part is reflected, some part is transmitted, and some part is reflected, and some part is transmitted. Do you get that? Now I talked about these rays, especially. We need to talk about this case only, especially at this case, there is a phase difference of pi created. If this is zero, everything else is zero only. All the other rays are zero only, except for this single ray, which actually created a phase difference of pi. Look at the other cases. Reflected from glass to vacuum. So glass to vacuum, glass to vacuum, glass to vacuum, glass to vacuum, glass to vacuum. This is the only one which actually came from vacuum to hit the glass. This is the only reflection. I hope I made sense here. So we are only talking about this ray 1 and 2, and we're talking about the interference. And then separately we talk about the interference of 3 and 4 in a different case. Let's just talk about the 1 and 2 interference case. Okay, so that's the reflected wave, reflected part interference case, and then transmitted part interference case separately. All right, I'm going to discuss the reflected part first. The wave is reflected and there is additional path traveled and like this, like between 1 and 2, the rays 1 and 2, this is the additional path which is traveled. Okay, we there are other rays also, of course, but because of the third reflection also, but this ray is, the amplitude of this ray goes very small, so we don't really need to consider this thing. The third ray, so like the amplitude has gone down already at the first ray, and it has gone down further at the second ray. It goes down very like to a very small value of the third reflection. So we don't really consider the third reflection. That's not that important. You can consider, but it won't still make much of a difference. So I'm talking about the interference between the first ray and the second ray. There is a path difference that you can see. Let us call the thickness of this glass slab is D. And these rays are almost traveled D and D. Like they are at an angle, I agree. But we can't really consider the angles at this moment. That gets way too complicated. So we don't consider the angles here. We just say this is D and this is D geometrically. Those two things are actually D and D geometrically. But what about optical paths? Remember optical path, like when a glass slab, if it is traveling outside after distance t, and if it is traveling in a glass of a distance t, it is mu t here, it is just t here. It is mu t here, it is t here. That is why this distance and this distance can be considered as mu d and mu d. That is the optical path difference. So the delta x between ray 1, ray 2 and ray 1 can be like the first ray is this, the second ray is like this whole thing is a difference, right? It is nothing but 2 mu d. The whole path difference between these two things is 2 mu d. That is where we came across. And there is already a phase difference of pi here. Not this angle. I'm sorry if I draw this as an angle as phi. No. The reflected ray already has a phase of pi. This already has a phase of pi. And this is an additional phase created. All right. So let us say this 2 mu d equal to 0 or lambda or 2 lambda or 3 lambda. Remember these cases, these used to be maximas in the previous case, right? In the interference, when the path difference is 0 or lambda or 2 lambda, 3 lambda, these were the maximas in the previous case. But in this specific case, what happens? There is all like this, because of this, there is a 0, because of this 2 pi, because of this 4 pi, because of this 6 pi are the path phase differences created, except because of reflection, there is an additional pi, which is added to all of those things. So final phase difference actually is becoming as pi, 3 pi, 5 pi, and 7 pi, like that. All these pi's are additionally added because of this reflection, right? I'm considering all the cases. So all these specific cases are actually become what now? They're all becomes minimas. If only the path difference equal to 0, lambda, 2 lambda, 3 lambda, they're all become minimas. That is a beautiful thing. About reflection, we are talking only about the reflection here. Let me write it. And similarly, if only the path difference is this time 2 mu d, the same path difference 2 mu d is lambda or lambda by 2 or 3 lambda by 2 or 5 lambda by 2 or 7 lambda by 2. For all these things, that it used to be a minimum. It used to be a minimum because the phase differences are pi, 3 pi, 5 pi, and 7 pi, like that. But because of this reflection, we add additional pi's to everything. Pi, 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 pi. So final phase difference, delta phi final in this case is 2 pi, 4 pi, and 6 pi, and things like that. Because of this, you are getting maxima. So in this case, all these things are silly, out of nowhere. They are considered as, sorry, not minimus, maximus. They are considered as maximas now. You see the change, you observe the change. This all happened just because of one simple thing, because of this pi. Because of that pi, all the lambda, 2 lambda, these things has become the minimas, and all these things are actually become maximas. Now this all interference is happening in the reflected wave. So I'm just going to give you an example. Let us say there is a glass slab, white light is reflecting, and rays are coming like this, reflected rays 1, 2, and I found 2 mu d, the path difference equals to some 5 lambda, where that lambda is lambda of red color or lambda of blue color, whatever it is. Let us consider that exactly equals. So they give you the value of mu, like 1.4. Let us say they give you the value of thickness, so some 3 millimeters. If only I calculate it, it is coming as some 5 lambda, and the lambda is actually a lambda of red. If only that happened, what will happen if it is 0 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, for all these things, they are actually minimas, right? They're all actually minimas. So in this case, it is 5 lambda, so it must be a minima. So in the reflected light, you do not see red color. The red color will be completely gone because there was a destructive interference. There was a minima of red since it is 5 lambda. If only the same value, the same 2 mu d for a different color is coming as 7 lambda by 2. Let us say this time lambda is actually green. Like you take lambda green, the value is coming as 7 lambda by 2. For this value, it must be a maxima. So if you put white light, you will not see any red light, but you will see some green light. So you in the reflection, you'll only see green light coming towards you, but not red light. Because for red light, it has become a minima. For green light, it has become a maximum. For red light, it has a destructive interference. For green light, it has a constructive interference. That is the biggest difference. I hope you get that. If anyone has any doubt or didn't understand up till this part, please raise your hand. Please, at this point, don't complain after the class. Or you can text me. That's also fine later. Okay. Who is coming now to Rumku Yashashwini? Okay, someone sent me a message saying, "Sir, from where does the red come? The white light includes everything. When I say white light, I'm talking about all the VIBGYOR colors. You are incidenting all the colors, and out of all the colors are reflecting also. All the VIBGYOR colors are reflecting also. But when red is reflecting, it is distracting itself. When green is reflecting, it is not. It is constructing itself. Dheeraj, do you get it now? Dheeraj asked a doubt. Okay, good. So you're actually, when you're incidenting white light, you're actually talking about all the colors incidenting on it, and all the colors are reflecting also. All the VIBGYOR is again reflecting also. But out of that reflection, red is being distracting by itself because of the path difference. Green is not distracting itself. So you see green, you don't see red. Of course, it applies for other colors also. Like you have to calculate for other colors also, whether it's a constructive interference or destructive interference, like that. All right. Now that we're done with reflection, let us talk about transmitted light. I call these rays are like 3 and 4, right? Even in between 3 and 4, the path difference is again 2 mu d only. Again, the path difference is 2 mu d only. But this time we are safe because there was no extra path difference created. If this is 0, this is 0, this is 0, 0, 0, 0, 0. There is no additional phase created. Everything is at the same phase. So because of that, if 2 mu d equals to lambda, 2 lambda, 3 lambda, 0 also, 4 lambda, 5 lambda, things like that, you can happily say they are maximas. If only 2 mu d equals to lambda by 2, 3 lambda by 2, or 5 lambda by 2, you can happily say they are all minimas. Things are simple now. All of them are maximas, and all of these things are minimas. So can you please tell me, if this is happening on the transmitted side and this is happening on the reflecting side, obviously the thing is, like if you see some light on the reflecting side, you do not see that light on the transmitting side, obviously, right? Because for the same idea, 2 mu d is, let us say 2 mu d is 5 lambda already for red color. For reflected light, if it is 5 lambda, it's a minima. So you won't see a red color there. But for transmitted, for 5 lambda, it's a maxima. So you clearly see red color. So you can actually do this experiment at your places, at your home. Like take a soap film, like create a soap film, okay, in your hands. Like put in white light. Like white light is nothing but sunlight or any light that is coming from your tube light also. Check the colors and from the both sides. Like check it from this side. You can observe some colors and go to the other side and clearly observe that the color that you can see from this side are missing on this side. You will see different colors from both the sides. Okay, that is the most interesting part. Okay, and all these examples that I was talking about, you can see that violet color, right? If you see on the other side, you will see a different color. And all these colors are Because of different thicknesses and different angles, you're looking at different colors. The light falling on the disk is actually nothing but white light, a combination of all the lights. But only from some part the light is reflecting, some part, for some part it is reflecting and creating a constructive interference. For some part it is creating a destructive interference, and that is why you are looking at the whole thing like that. All right. So, and in thin film interferences, questions asked like this, like they give you the mu value of that film, they give you the mu value of the film, and they give you the thickness of the film or slab or whatever it is, and they ask what are the wavelengths that are missing in the reflected light. Sir, is it applicable only for glass slab? No, it is applicable for anything. It is applicable for anything, but we only consider glass slab because it is purely transparent, right? Since the glass slab is transparent, you don't see any other colors coming out or going in. So you can kind of have a transparency. That is why you only use a glass slab. And soap film also, it is also clearly transparent. It is actually applicable for anything. You can use that anything, so that for anything, but as long as it is as transparent as these two things. So it simply asks you which wavelengths are missing, for which wavelengths it is minimas in reflection and maximas in reflection, and for which wavelengths it is minimas in transmitted light and maximas in transmitted light. They might ask these questions. If you can find this will be automatically found, right? It's not a big deal, in my opinion. So that is the idea of thin film interferences, guys. Okay. Now, I just wanted to show you this also, obviously. Like, look at this case. There is a glass slab. A wave is going through the glass slab. The wavelength is clearly changing there. The wavelength is clearly changing there. Don't you think? Now, I'm considering the first reflection. Or what happened? This thing already hanged. Let me just start it again. Don't worry. Yeah, this one. So this is the wave that is incident on the glass slab. It is changing its wavelength inside the glass slab, and it is changing back to its original wavelength outside, right? Let us look at the first reflected wave. This is a reflection at the first surface. And this is a reflection at the second surface. Now we are going to talk about the interference of these two, the first reflection at the second reflection. I'll just take a screenshot so that you'll understand it better. So the light is coming here, falling on it. There is a reflection here and light went in there, and there is a reflection here and coming out. So we are going to talk about the interference between these two things, which is nothing but the green one and the red one. You clearly observe it for a bit, what exactly is happening in between the interference. You can clearly see that they're completely out of phase. Observe it. The green one and the red one. Only look at the green one and the red one. They're completely out of phase. So if I look at the resultant, look at the resultant. The resultant is almost dead. That is a complete destructive interference there. They are not the colors. They're just represented with different colors. Okay, they're not the original colors of the wavelengths. Okay. So the violet thing, the thing that the wave that is the resultant of the first reflection, the second reflection is almost dead. Now let me change the thickness of the film just for fun. Look at it. For some other thickness, you're getting a maxima, and for this thickness, you're getting a minima. Can you observe that, the whole thing? And for other values, you'll get always a different resultant. Like for this case, you're getting a complete minima. Look, the thickness of the film, in the top it is written as the thickness of film is 1 lambda. And the thickness is exactly 1 lambda, like you're creating path difference of 2 lambda. We know that for 2 lambda it is a minima, right? So for 2 lambda it's almost a minima. And let us check for 1.5 lambda, shall we? Wait. I will check for 1.5 lambda just for fun. Yeah. It's not exactly working. I'm sorry about that. It is actually coming at us 1.17 lambda because of the refractive index also, right? I forgot about the refractive index. It's not just about the thickness, right? So anyway, so if I have the incident wave and the reflected wave and the resultant, I can clearly observe that for some thicknesses and for some U values, you're getting a maximum a constructive interference and a destructive interference. Okay. I hope this simulation actually helped you. There is no simulation for transmission there. I'm sorry about that. But even transmission also, you can clearly understand. And even if he had a transmission simulation there, this is the incident, right? If you are getting a minima in this side, in a specific case, you would have definitely got a maximum on that other side. That's what we've seen right now. So that is a observation that you need to remember. Okay. So that is it, guys. That is the idea of thin film interference. I just wanted to completely discuss that idea. So once we are done with that, we need to start ourselves with a very big, beautiful idea, which is really, really important. The core idea of this topic. It's like the most important idea of this topic. Most of the people neglect this topic because they think it is difficult, but I'll show you some beautiful ideas about it. I hope it makes sense to you. This is a very important idea. Please do not neglect this thing. Diffraction. What exactly is diffraction? I've already shown you some examples for diffraction, remember? Yeah, that is nothing but diffraction. That thing, like the waves on the other side. So when you have a small hole, a single hole, and waves are coming towards that hole, we might actually expect that the waves should actually come through the hole only. And we have a screen over there, let us say. The light should actually fall only on the screen up to this point. But what is actually observed in the real world? It's not like this. It's actually that the light is actually distributed a bit more outwards. Like, why exactly is this happening? We've talked about it. We've talked about the idea of it using the what principle? Young's principle. Sorry, not Young. What was that? Huygens principle. I'm sorry about that. When we talk about Huygens principle, all the sources again act as multiple sources now. So the resultant of all these things actually come like this, and you will get additional waves, and that is exactly what is happening here. Check. Okay, all the points at the hole are actually again behaving as sources, and looks like it is actually spreading out. This is the very reason why you can hear sound, even like when you're in a room and there is a small hole and there is a sound source. Even when you're here, you can hear the sound, not even if you're not in the line of sight, because the sound actually diffracts very much. The diffraction of sound is like very, very high. So the sound actually can be heard by you because of this only. And I've shown this example also that day, I guess. Wait, not that one. Yeah, this example. The reason why you can look at the light even though you're not in the line of sight, because the line of sight is clearly visible there. I can't, wait a second. Yeah, this is the line of sight. Even if you're not in this line of sight, the light is actually diffracting outwards and it is actually reaching you. That is why you can see that light. Okay, these are the ideas of diffraction. Okay, that is a practical knowledge about diffraction, but we're not done with practical knowledge here. We want some theory also, like what exactly is happening in a diffraction. What are the kind of things that are we needed to observe in a diffraction. Okay, I will show you that. So when you have a single hole and you have a source, the kind of diffraction that you actually observe goes like this, like the intensity. I'm directly taking you to the intensity diagram. I will explain how this works later. Okay, the intensity actually goes like this, not just in the line of sight. I'm sorry, I'll draw it again, don't worry. I'll take a very small hole. And the source. Okay, this is the line of sight. But this light, the intensity just doesn't, of course you will get a maxima, but the maximas actually get like this. The light actually looks like it's spread up to this point. This is the, sorry, the screen is not working. Oh, Tejas Ambedkar said the screen is it working, guys, right now? The screen is working, is it? think it is. So it actually spreads not up to this point, up to this point. And the best part is it's not even stopped here. There are fringes outside also. So you actually see not just a central maxima and a minima. This is a central maxima. And you observe a minima. And then you get some maximas and minima and maxima and minima and things like on both the sides. Why is that happening? Now, you can actually observe that in your daily life also. Like you put a screen, you put your hand right next to the light. What do you observe there? What the most important thing that you observe there is like the shadow that you're looking at your hand is not that sharp, that there's actually a blurriness. The shadow is actually spreaded there. So that is the kind of observation that you need to see here also. It's not that the light is only spreaded up to this point, it is spreaded. And it's not just that you're actually getting extended things, right? You're actually getting extended patterns. That is a most beautiful thing about diffraction. Okay. So I will take a simple specific case about diffraction and let us just read it, like what exactly is happening there. Like how do you actually talk about intensities in this case? How do you talk about maximas and how do you talk about minimas in this case? Let's just go there. Okay. So what I say is when you have a hole and the light is coming, I just consider that there are multiple sources here, S1, S2, S3, S4, S5, infinite number of sources there. So at the center, of course, the path of every source is coming and they're all just simply making a huge constructive interference. They're all creating a huge constructive interference. That is the reason why you're getting this big of a constructive interference there. But what happens after that? Not at this point, but what happens up at a point which is not that. Not at this point, somewhere around here at a distance y again, which is making an angle theta. 1, 2, 3, 4, and infinity. Just count as many as possible. The point is, like when I'm drawing a perpendicular, look at the path differences here. There is some path difference and there is more and there is more and there is more and there is more. The path, there are infinite number of sources first of all, and the path difference keeps on increasing. How do you approach at this problem? Like how do you find the intensity when there was just two holes in thin double slit interference, and it was just simply two holes. I'm sorry, I can't draw it here. I don't know why I did that. When you have just two holes, all you have to do is like write the path difference between these two things, which is nothing but d sine theta, and d sine theta is n lambda. That's a maxima. If it is n plus 1 into lambda by 2, that's a minimum. We simply did that because we only have two sources. But look at this case. We have multiple sources here. How are we going to do this? We are going to use a brilliant idea here. Let us call this angle theta. So this becomes d sine theta if this is d. Not rocket science, right? If this is theta, if this is d, this is nothing but d sine theta. So I'm saying the path difference between the first source and the last source is d sine theta. The path difference between the first source and the last source is d sine theta. Now let us come to the first source again, and let's look at the second source. The path difference is very, very small, and it increased a little more, and it decreased a little more, and a little more, and a little more. So what I'm going to do is I am going to put them all on a vectorial representation. How? Like this. The first source amplitude is this, a small arrow. The second source amplitude is increased. I mean, not increased. The angle is a bit more. And this is just a vectorial representation. I'm telling you guys. Okay, let me just draw it here only. And the third source is here. The fourth source is here. The fifth source is here. The sixth source. Just like that. Until which part do you actually draw? You don't have to draw all the things. I will actually give you a simple idea. If this d sine theta equals to n lambda, or let us say if this d sine theta equal to 3 lambda, what does it mean? The phase difference is 6 pi. The phase difference between the first one and the second one is last one. First one and the last one is 6 pi. So what I'm going to do is I will start here at S1, S2, S3, S4, S5. I will go one full round. that is 2 pi. I will go the second full round, that is 4 pi. I will go the third round, that is nothing but 6 pi. So the S final, S first one and S final one. I'm talking about S final here, I'm talking about S first one. If I just rotate it 3 times, I'm actually considered all the things. I've actually considered the whole phase difference. So let me not go that far. Let me just take you a smaller example. Let us just say the d sine theta equals to 0.5 lambda. 0.5 lambda means the phase difference is pi. You remember that, right? 1 lambda by 2. Lambda by 2 is nothing but pi, right? So the first one goes here, second, third, fourth, fifth, sixth, seventh, eighth, and last one actually goes here as final. As simple as that. If only this thing is not lambda by 2, it's actually lambda by 4, which means pi by 2. The phase difference is pi by 2. So the first one goes here, S1, S2, S3, S4, S5, S6, and then S final actually goes here. That's it. So what I just told you is just to represent the path difference in a phasor diagram. Now the important part comes. How do you find the resultant? What I'll do is I'll just simply represent these whole vectors. Can I represent the vectors like this? S1, S2, S3, S4, and S final like this. And we all know that the resultant is nothing but this vector. You all know that, right? Once I represent all these things in a vector form, this is nothing but the final resultant. So if only this is S1 and this is 2, S3, and S5, this is S final, the representation actually simply goes like this. And this goes the resultant. All right, you get my point. So as I'm changing the angle, as I'm going up, as I'm changing the angle, the d sine theta is changing. The d sine theta is changing along with the angle. If the d sine theta is changing, the phase angle difference is changing. If the phase angle difference is changing, this is changing. If that is changing, the resultant is changing. Okay. Now I'm going to show you something beautiful. Watch this. I'm going to consider the midpoint itself. Where the path differences are 0 completely. The phase difference, the path difference are completely 0. So S1 is like this, S2, S3, S4, S5, S5, everything must be same, like they're all in the same phase, S final. So this is the resultant, that's all. So if only I consider the amplitude of one small source as A0, everything is just A0, 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 A0 only. It's like the amplitude is just like the total amplitude can be simply considered as like a sum of these things. But they don't actually consider it as A0. They consider the sum value so that the resultant is actually A0. The final resultant of all these sources, the total length is considered as A0. Let us consider a small angle. Let us take a very small angle. Here, this is creating d sine theta. Let us say that is creating some phi. Let us say that I represent the phi in a phasor diagram. 1, 2, 3, 4, 5, 6. And the last one actually gives an angle of phase. So this is a resultant. And that is how the resultant is represented. Can somebody tell me this, if this is representing the central maxima, let us say like this is the central maxima, right? This is what we're talking about. What does this represent? Like, wait a second. I don't want to discuss that yet. Yeah, let's just check this. So as I'm moving on at the center point, this is a diagram. At the center point, this is a phasor diagram. As I'm moving on, the phasor diagram is like slowly closing in. And at some point it actually closes in like this. I will show an example, don't worry. At some point it actually closes like this. When does it actually close in completely? When S initial and S final are the same angle, which means S1 must go like this, S2, S3, S4, S5, S6, S7, and they go on, and S final actually must give you an angle of the same value. It means you're actually turning an angle of 2 pi, which means the path difference If you're talking about 2 pi, the path difference must be equal to lambda. You're getting my point? The path difference equals to lambda, which means this is nothing but d sine theta. So if only you get d sine theta equal to lambda, look at the resultant. Look at it started here and it ended here. What is the resultant? 0. The resultant is coming as 0. You getting my point? If only d sine theta is lambda, lambda is creating an angle of 2 pi between the first source S1 and the final source. If I put it on a phasor diagram, the resultant is clearly coming as 0. So that is where I observe the first minima. So this is a central maxima, right? But at that specific point of this specific point, I get this d sine theta exactly equal to lambda. The minute you get d sine theta equal to lambda, you're creating a phase difference of 2 pi between the first source and the last source, where I have to draw the diagram like this. All the sources curl up and end up at the same point, and you're getting a resultant of 0. That is how I find the resultant. Now what happens after? What happens? I go beyond that point. Like, not this point, I go beyond that point. Like, let us say next point. So this time the d sine theta is more than lambda, so it is more than this angle. So what happens is the vector resultants actually curl up and don't end up here, they go on further. And they go on further and other and further and further and further. So I will show you. This is a central maxima where all these things are actually creating 0 phase difference. This is a central maxima. I'll show you the resultant when this is happening. When one circle is happening, that is the first minima. And when this happens, this is the first maxima. Because central maxima is over, this is the first maxima. This is the point where you can get the next maxima. And like when it is rotated twice, I'll just show it on the simulator. It's quite easy that way. Yeah, here it is. Watch this thing. This is really beautiful. I'm sorry, it's RA. This app is torturing me, man. But again, this is one of the best apps right now. Watch this thing. When I change the angle, look what's happening to that thing. At center, I'm getting the maximum. At center, I'm getting the maximum. At the center, I'm getting the maximum angle. This is the central maxima. You observe that? And I change the angle. It is curling up, and it is creating a 0 amplitude exactly at that point. Again, it is curling up to 1.5 circle, first maxima, 2 full circles, second minima, 2.5, 3, 3.5, 4, 4.5, and things like that. It's getting smaller and smaller. Isn't it beautiful? This is the central maxima where all the amplitudes are just lining up, and other side also, on the other side also. At this specific case, it is creating exactly the first minima, first maxima, second minima, things like that. They just go on further and further. That is why the amplitude is getting smaller and smaller. Isn't it beautiful, guys? So here the resultant amplitude is considered as A0. Okay. If you're happy with that simulator, let's just go forward. Okay. So what if I'm not talking about the first maxima or the central maxima? I'm talking about some random point at an angle theta. At some random point. How do you find? You have to find d sine theta. Because of that, you get delta x. From that, you get delta phi. Because of that delta phi, you get some random angle, right? This is a random angle. This is delta phi, let us say. You have to find this resultant. How do you find this resultant? It's as if This is the central maxima. The total length of the central maxima is A naught. We already talked about it. The same A naught has actually curled up, and you have to find this as a resultant now. This was the initial case where the total length is A naught. Now we have to find this length. We actually use a basic mathematics here. Okay, I'm just going to show it to you. This original length is at the central maxima where it is A naught, and the same thing actually curled up like this between an angle of delta phi. The last one and the first one has an angle of delta phi. The resultant is nothing but this. This is the resultant. All right. So I'm going to write some radius. I know the length of this thing is nothing but A naught, like the length of the specific bit. This is the A naught, and the same thing is also A naught. I write, if this is delta phi, this is also delta phi. Basic mathematics. So can I write A naught equals to R delta phi? A naught equal to R delta phi, L equal to R theta. Arc length, right? So from that I write the radius of this that curve that I'm looking at is A naught by delta phi. Radius of that thing is A naught by delta phi. But we don't need the radius, we need the resultant, right? We need the resultant. How do you find this resultant? In a triangular law, R, you have angle. This is nothing but R sine theta. Do you agree? So the final resultant is R sine, the theta is nothing but delta phi, and R is nothing but A naught delta phi. Is the color fine with you? Sine delta phi. No, I'll just write it in white so that it is visible. The resultant has come as A naught into sine delta phi by delta phi. Now that I'm getting here, now that I've got here, you don't need any of the things that I just explained. Even if you don't understand any of those things, just finally remember this answer. The resultant amplitude, I'll just give it as a formula. Resultant amplitude equal to A naught. A naught is the amplitude at the center into sine phi. From that I write intensity. Resultant intensity equals to I naught. Since I have to square the whole thing, right? If I square the whole thing, I naught sine square delta phi by delta phi square, of course. This is the answer that they are going to ask. No, they don't even ask this answer. What they ask is, they simply ask you where does the first minima occur. Most of the problems, like in the most of the single slit diffraction, they ask about where the single slit, like where does the minima occur. Where does the minima occur? D sine theta equal to lambda. That's it. That is where the minima occurs. So in the place of the sine theta, you simply put a y by L again, like yesterday, and you find the y value. That's it. They are going to ask this thing at the most of the times. Like, why did I explain all these things? Because it is good to understand. To understand all these things is like really important thing. That is why I explained it. In the end, all they are going to talk about is this intensity formula, and they might ask you the y value, d sine theta equal to lambda. That is where the first minima occurs. All they care about is the first minima only. They don't even care about the central maxima. They don't care about the first maxima, second maxima, things like that. In single slit diffraction, in single slit diffraction, there is only one hole and the diffraction is observed. No one's actually going to care about the other interferences where there is second maxima, third maxima, things like that. They only care about the first minima as long as the mains problems are involved. The main level problems are only involved about the first minima only, nothing more than that. So if you haven't understood about what I told you for the past half an hour or more than that, don't worry about it. It's totally fine. All right. Now, is there anything that I wanted to show you in diffraction? Yeah. Of course, I will. Let me show you something else on diffraction. Go. Suppose you are stuck again. Thank you very much. Beautiful app. Yeah, look at the diffraction. I can change the values of d here, which is nothing but the thickness of that thing, and observe different interferences. Look at the value. If I change the wavelength, the color is also changing. You get different diffractions. Like this is a source, and that thing in the middle. I'll just show it to you also. This is the source here. This is the slit, and the light is falling. You get the central maxima, first minima. There is first maxima, minima, and first maxima and minima, and nobody cares about them. Okay, they only care about. If you clearly look at it, it should actually spread up to this point only, but it clearly spread it up to this point. Like you see a bright light until this whole space, and it goes dark after getting a few fringes. Okay, that is what that you need to care about. Now, if only I give the double slit experiment here, like I give two slits. Look at it. I'm giving you two slits now. But this is not like the thing that we learned yesterday, right? Yesterday, when I talked about double slit interference, we simply said, when I said Young's double slit experiment, we simply had the fringes like this only. Like all the intensities are same. Nothing changed. But out of nowhere, now I'm giving you another diagram like when I give you two slits, I'm giving an interference like this. How come that happened? What about yesterday? Did I lie yesterday to you? Yeah, why? This is the truth. This is the reality. This is what happens. But if I teach you the both the things yesterday only, it gets really confusing. That is why yesterday I taught you people saying this is just happening. Like in single double slit diffraction, this is only observed. But when there is single slit also, like but each one is a single slit again, right? So because of this there is diffraction, because of this there is diffraction. So effect of diffraction and interference, both the things occur, and the final original reality is this. You will observe interferences, but they will slowly go down. That is how the diffraction and interference, a combination of those two, both the things actually appear. Okay, guys. So that is the idea of diffraction, and all the things that I wanted to show you, I've already shown you. What happens if I have multiple slits, like more slits? Let's say let's just check if I can create more slits. Phew, this app is torturing. It's fine. Let's just leave it. If I give you more slits, the interference gets more complicated. That's all. Okay. You don't really need that. All you need to talk about is Young's double slit interference and diffraction due to single slit. If you don't understand any of those things, just remember the formulas. Just go with the formulas. They're totally fine by as long as it goes for the mains level questions. They're totally fine. All right. Now after this, the diffraction idea. Of course, there is one more thing. There is circular diffraction also. Like they put a circular hole. They put a circular hole and they try to observe the diffraction. In this case, let me put a smaller hole there. Okay, it's not a slit. There is a difference between slit and a circular hole. Okay, in a slit, it is vertically just cut like this. This is a hole, a vertical hole. That is called as a slit. Here we're talking about a circular hole like this. There's a difference between the circular hole and a vertical slit, right? So in this circular hole also, like when you put source, you should see a very big circular brightness on the screen. But this also doesn't happen. The brightness actually spreads over, and then like in reality, what happens is you get a bright circle in the middle, and then obviously you see fringes around that thing. Okay, uh, let's see if I can find the image for that. Circular diffraction, let's just check it as circular diffraction. Okay, circular diffraction. Yeah, this is a circular diffraction. This actually happens in real life. Okay, But yeah, I had totally forgot to mention that in most of these experiments, they use lasers, especially because the laser light doesn't have a range of wavelengths. Like when you put white light and try to observe the interference, what happens? You get red maximum at one place, violet maximum at another place, and blue maximum at one other place, and green maximum at different places. Because of that, what happens is like you can't really observe which maxima is there and which maxima is there and isn't there. Okay. So what we do in these cases is we actually put a laser there. When you put a laser light, the wavelength is like very limited to a specific value. So in these cases, we can happily observe the interferences. That is why we need a laser there. So when you put a circular hole, this is the kind of this is the kind of interference that you actually see. And I'll just explain it here only since it is clear. Uh, in reality, it should only have spread up to this point, but it's actually spread up to this point. So what they do is like they do a mathematical method, but it is not there for you. They take all the sources here, they try the interference of all the sources and do it, but don't worry about that. All you need to worry about in that case is uh, the angle that they measure. Like when you have a circular hole, at until which angle it's actually spread, and the angle is goes as was sine theta equal to 1.22 lambda by d. Just remember this formula. You don't have the derivation why you got this thing. It is a very complicated mathematical method. Okay, all you have to do is just remember this thing, or like just remember this bit. There will be path differences, right? Just like that, we had a single slit diffraction. To get the first minima, you had d sine theta equals to lambda, right? Here, just like that, like you write the path differences only, but here if you write d sine theta, it must be equal to 1.22 lambda. Just remember this value, 1.22 lambda. If it is lambda, that is a minima there. If it is 1.22 lambda, you get the first minima in this case. This is a a circular disc, a hole diffraction. Let us just call it as circular hole diffraction. Remember this idea. This is also a very important idea. Okay, circular hole diffraction also is a very important idea. Just remember that thing. Now, linking onto this thing, there is a very important idea, guys. Watch it. There is a topic called limit of resolution. This is also a very important mains level and answer level topic. Mains level and answer level topic. This is a very important topic. I'll tell you what it is. The problem is, like I'll just show you a practical example. Have you ever been on a road and you see a car coming towards you, but the car lights actually look like this? They're completely blurred. There are actually two lights, but you actually see them as a single light, completely blurred. I'll tell you the difference. I'll tell you why it actually happens. Okay. So you have two sources, two lights, source one and source two, and you have your human eye. We've talked about it, and human eye also there is a small hole, right? We call it as aperture. So this small hole is nothing but this hole here. We actually compare this whole thing with that. This source creates an image on the back of your retina, and you get a intensity like a pattern like this. And because of this source through this hole, you get an intensity pattern like this. Now, when these two things are completely separate, you will see them as separate sources. But what happens when these sources are like really close? When the sources are really close, they form images, intensities which are really close. I'll just show it to you on the graph. Yeah. Look at this case. I'm going to separate them by a small value. Wait, no, not that. Look at that. As long as they're like this, you can happily see them as two separate things. But as the separation is getting decreased and decreased and decreased, they almost look like the same thing. They almost look like they're forming a single image. That is when you actually see them as a single source. That is a problem why you actually see them as single thing. That is the same problem when I put two dots on a whiteboard. which are like really, really close to each other. They almost look like they're a single dot, right? That is a problem. They actually form two images in our eyes. They actually form two images, but because of the diffraction, the two images come really close. And at that specific point, you don't actually see them as two separate images. You actually see them as a single image, and that is a problem. Okay. So they actually bring a criterion saying that the separation is totally fine here. If it is like that, you can happily see them as two images. Even now, you can happily see them as images. Even now also, you can happily see them as images. But at this point, what exactly am I talking about? At the minima of the first one comes the maxima of the second one. If this is the minimum separation between them, this is the point, this is the final point where you can see them as two separate sources. Beyond this point, he simply says, beyond this point, you can not see them as two separate things. Like once I cross this bit, like they totally looks like a single thing anymore. Beyond this specific point. Okay, so that is what they say in that topic of Rayleigh's criterion, minimum limit of resolution. That is called as, I already put a heading, right? Limit of resolution, and they say that you need a minimum angle of that. That angle is nothing but this again, like that we have here. That angle sine theta or theta, which is really small. So if it is 1.22 by lambda by d, they give you the value of lambda that is coming from the sources, and d is nothing but the aperture size. If this is angle, if this is the angle that is maintained there, these are sources, this is the eye, this is the aperture, and this is the angle again. This is the theta and this is the theta also. If this is the theta that is maintained, as long as this theta is maintained, you can see them as two separate sources. If you go beyond this theta, like if the theta is less than this thing, you cannot see them as two separate sources. That is what he says. So they actually give problems like there are two light sources which are at 1 meter apart, and they are at a distance 20 meters from the observer. So they simply say, what can he actually observe them as two separate sources? You simply check theta equals to 1 meter by 20. Just check whether this value is 1.22 lambda by d or not. If it is more than that, if it is greater than that, he can happily see. If it is less than that, he cannot see them as two separate images. This is called as limit of resolution, guys. All right. The class is already long. Is it fine? Like, can I continue? If you think I've covered too much by now, I'll just introduce a new idea and just I'll just introduce that idea tomorrow only. We can do the problems tomorrow. Someone's saying the class is long. I agree, Dheeraj. The class is long already. So I'll just introduce the idea of polarization tomorrow. Okay, I will just introduce this idea tomorrow. But today you'll have to do the Young's double slit experiment problems already. Okay, there is Young's double slit that you need to do, and then there is single slit diffraction that you need to do. If you don't understand the single slit diffraction, just go with the formulas. There you can find the formulas right there in HCBAM. I'll just show it to you. Here, this is the limit of resolution that I just talked about. Clearly watch, well resolved, just resolved, unresolved. Okay, so that is what the names that they call them as. And there is this formula for circular diffraction, circular 1.22 lambda by d, and the intensity formula is right here, you can see, and the maximas and minimas. If b sine theta equal to lambda, first minima is occurred. If b sine theta equal to n lambda, the dark fringes occur. So you can happily follow these formulas and do these questions. Okay, and there are a few ideas that I've skipped. I will discuss them once you are completely clear about all the basics. Okay, and there is polarization that I need to discuss. Before polarization, you can do all the problems. Tomorrow I will complete polarization and I will discuss the problems from H.C. Varma. And guys, please make sure you read through these questions. Which questions? Wait a second. Questions for short answers. I am going to discuss these questions tomorrow. You will have to speak one by one. Okay, you people have to speak one by one. Right, class notes for wave optics. I will have to get it from seniors. I don't have it right now. I will get it and I'll give it to you people. Okay. look at go through these questions for short answers, questions for short answers. You don't have the answers, you just have to give me the answers tomorrow. All right, so go through these questions. I am expecting some people to speak tomorrow, so if I don't see some hands rising, I'll be very disappointed. You don't want to see me disappointed. Objective 1 and objective 2, just go through these questions and we will discuss them tomorrow. All right, so thanks so much, guys. I think today's class is a bit difficult thing to understand, but if you understand it, it's really easy. Okay, but the formulas are really important for the mains and AMCET questions. Okay, but the idea, the whole core idea, is important for the advanced level exam. All right, guys. So thank you so much, and I hope I'll meet tomorrow again. We'll wrap up this topic tomorrow. The topic will be over tomorrow. That is for sure. If anyone has anything to say, you can raise your hands. Nothing? All right then. So thanks so much, and we will meet again tomorrow. Bye bye.